We'll start in about 1 minute. Today and Wednesday, we will review for test 3. Test 3 is this Friday over the chapter 3 material. I'm going to put a quiz 11 as a Moodle assignment, and I'll send an email later today with information about that. The playlists that also cover test 3 material are on YouTube. So note you can look for those on the YouTube channel. The test review problems that I do today and Wednesday, they'll be the same types of problems that are on the test 3 review sheet videos, but they're not exactly the same. So you can get more examples if you watch those videos also. Okay, we'll start reviewing in section 3.1 on inverse functions. There's an analytic way to show that a function is or is not one-to-one. So we'll use that analytic test on this one, f of x equals 2x plus 3 over x minus 4. What we do is we begin by setting f of a equals f of b, and then if we can show that a equals b, and only a equals b, then that function is a one-to-one function. F of a is 2a plus 3 divided by a minus 4. We set that equal to f of b, which is 2 times b plus 3 divided by b minus 4. And then we can use cross products or equal, or just multiply both sides by the least common denominator. Either way, you get 2a plus 3 times b minus 4 equals 2b plus 3 times a minus 4. Multiply the two binomials on the left, we get 2ab minus 8a plus 3b minus 12, and that's equal to the product of the binomials on the right-hand side, which are 2ab minus 8b plus 3a minus 12. Okay, so both sides have 2ab, so if we subtract those from both sides, those are eliminated. And both sides have minus 12, so if we add 12 to both sides, those are eliminated. And we're left with negative 8a plus 3b equals negative 8b plus 3a. And then we can do a couple of things at once. We can subtract 3a from both sides and subtract 3b from both sides. And we'll get negative 11a equals negative 11b. And then finally divide both sides by negative 11. We get a equals b. So this shows that f is a one-to-one function. That means that its inverse is also a function. Okay, in the next example, part B, g of x equals x to the fourth plus x to the second. So we recognize this degree 4 polynomial function as a function. We know ahead of time that it's not one-to-one. So if we can show by example, for example, if we say G of 2 is 2 to the 4th plus 2 to the 2nd, or 16 plus 4, or 20. And also G of negative 2, which is the number negative 2 to the 4th plus the number negative 2 to the 2nd is also 20. And then note that the domain values are not the same. 2 does not equal negative 2, but they each give us the same range value. So G is not a one-to-one function. It violates the definition of a one-to-one function. Okay, then in the next example, in this one, k of x is a degree 3 polynomial function. We know that not all degree 3 polynomial functions are one-to-one. We know of degree 3 polynomial functions that fail the horizontal line test, but some degree 3 polynomial functions are one-to-one functions. So let's test to see if this one is or is not. We can start by setting k of a equals k of b. And k of a is a plus 2 to the 3rd minus 5. Set that equal to k of b, which is b plus 2 to the 3rd minus 5. Add 5 to both sides, and we get a plus 2 to the 3rd equals b plus 2 to the 3rd. And then if we take the cubed root of both sides, we get a plus 2 equals b plus 2. And then subtract 2 from both sides, we get a equals b. So this particular degree 3 polynomial function is a one-to-one function. It's one of those that this one would have a graph that looks something like this. It levels out and then it starts going back upwards. So it doesn't fail the horizontal line test, so it is a one-to-one function. In the next sheet, more about inverses. So on this one, determine if f of x equals 2/3 x plus 1/3 and g of x equals 3/2 x minus 1/2 are inverse functions of each other. Okay, so an analytic test, if we compute f of g of x, that is, if we compose f with g. So this means in the function f, we're going to replace every x with what g of x is. So f of g of x is equal to 2/3 times what g of x is. So 2/3 of 3/2 x minus 1/2, and then plus 1/3 on the outside. And then we do the arithmetic. 2/3 times 3/2 x is 1x, or just x. And then we're subtracting 2/3 times 1/2, which simplifies to minus 1/3. And we have a plus 1/3 on the right-hand side. So x minus 1/3 plus 1/3 equals x. Okay, so that's 1/2 of the test. But we have to compose the other way, g of f of x. And if this also equals x, then that means that f and g are inverses. So g of f of x, this time in the function g, we're going to replace every x with what f of x is. So g of x is 3/2 x minus 1/2. So g of f of x is 3/2 times f of x, which is 2/3 x plus 1/3. And then we have a minus 1/2 on the outside. And then do the algebra and arithmetic. 3/2 times 2/3 x is 1x. And then plus 3/2 times 1/3 is plus 1/2. And we have a minus 1/2 outside there. And this simplifies to x. So since f of g of x equals x and g of f of x equals x, this shows that f and g are inverses of each other. Or just f and g are inverses for short. Okay, in number 3, we find the inverse functions. In part A, find the inverse and the domains and ranges. So for f, we can, since it's a rational function, we can tell by looking what the domain is. The restricted values from the denominator determine how to find the domain. So there's only one restricted value, it's -2. So the domain is every real number except -2. So it's in interval notation, -∞ to -2, parenthesis, and then union, parenthesis, -2, infinity. Well, with a little practice, this particular rational function, you can tell what the range is. And I'll just go ahead and write down what the range is. And when we find the inverse, remember the domain of the inverse is the same as the range of this function. And then we'll be able to verify that it's correct or not. So I'm going to say that the range of f is every real number except 3. So -∞ to 3, parenthesis, union, parenthesis, 3, infinity. Okay, but now we find the inverse. Replace f of x with y, so we get y equals 3x minus 1 over x plus 2. Then interchange x and y, so we get x equals 3y minus 1 over y plus 2. And then multiply both sides by the least common denominator, which is y plus 2. So I'm going to start the work over here. So we get the binomial y plus 2 times x equals 3y minus 1. We want to get every term that has y in it on one side and every term that doesn't have y on the opposite side. But first we have to multiply y plus 2 times x, so we get yx plus 2x equals 3y minus 1. Two terms have y in it, and the other two don't have y, so we'll subtract 3y from both sides, and also subtract 2x from both sides. And then factor y out of those terms, so we get y times x minus 3 equals -2x minus 1. And then finally, y equals -2x minus 1 over x minus 3. This is equal to f inverse. Okay, the domain of f inverse, so f inverse domain, it's every real number except positive 3. So -∞ to 3, parenthesis union, parenthesis 3, infinity. And that's the same as the range of f, which we already noted. And then the range of f inverse is the same as the domain of f. So the domain of f is every real number except -2. Okay, so that covers part A. Part B, the square root, g of x equals the square root of x plus 2. So since it's a square root, we want the radicand to always be non-negative. So that means x plus 2 is greater than or equal to 0, which means x is greater than or equal to -2. So the domain of G in interval notation, it's bracket -2 comma infinity. We can tell what the range is just by what we know about square roots, and the radicand is linear. X plus 2 is a linear expression. So when x is -2, the square root of 0 is 0. So the range has the smallest number. Notice that this is the positive square root of x plus 2. So the smallest range value has to be 0, and all of the other ones have to be positive because it's the positive square root. And then for values of x greater than or equal to -2, x plus 2 goes to infinity as x goes to infinity, and the square root of positive numbers that go to infinity also go to infinity. So the range is from 0 to infinity, including 0. Okay, to find the inverse, just replace g of x with y. Y equals the square root of x plus 2. Then interchange x and y, so we get x equals the square root of y plus 2. Then we want to solve for y. Since y is inside the square root, we square both sides. We get x squared equals y plus 2. And then subtract 2 from both sides. Y equals x squared minus 2. This is G inverse. Okay, but G inverse, even though it's equal to x squared minus 2, it's not a full parabola. So we should note what the domain of G inverse is. It's the same as the range of G. So its domain is from 0 to infinity, and its range is the same as the domain of G, which is bracket -2 comma infinity. Okay, we'll move on then to section 3.2. Okay, section 3.2 is on exponential functions. So we'll graph each function, find the intercepts, then find the inverse functions. Okay, but first note this exponential function, f of x equals 3 to the x minus 1. The exponent is x minus 1, and then plus 2. So this tells us, or this indicates that there's a y equals positive 2 is a horizontal asymptote in the negative x direction. So we'll keep that in mind when we're graphing. And since the exponential term is base 3, we'll pick our x values that will help us out with finding the corresponding y values. So if I start picking x values, you can pick any x values you want, but I'm going to start with x equals -1. Then to find the y value that goes with it, I replace x in the function with -1. So I get 3 to the -1 minus 1, which is 3 to the -2. 3 to the -2 is 1 over 3 to the positive 2. And 1 over 3 to the positive 2 is 1/9. And 1/9 plus 2 is 2 and 1/9. Okay, so this is just above the horizontal asymptote y equals 2. So this graph has to be entirely above the horizontal asymptote. Okay, then I'm going to pick integers greater than -1 consecutively. So the next integer after -1 is 0. In the function, replace x with 0. 3 to the 0 minus 1 is 3 to the -1, which is 1/3. 1/3 plus 2 is 2 1/3. This is a little bit higher than the previous point, but it's still above the horizontal asymptote. Then pick x to be 1. Replace x with 1. 3 to the 1 minus 1 is 3 to the 0. 3 to the 0 is 1, and 1 plus 2 is 3. And then a couple more points when x is 2 and when x is 3. When x is 2, the exponent 2 minus 1 is 1. 3 to the first is 3. 3 plus 2 is 5. So the ordered pair 2, 5 is a point on the graph. And then finally, when x is 3, 3 to the 3 minus 1 is 3 to the second, or 9. 9 plus 2 is 11. Okay, so we can plot those points. And then keep in mind that to the left of the y-axis, y equals 2 is a horizontal asymptote. Okay, so -1, 2 1/9. 0, 2 1/3. 1, 3. 2, 5. 3, 11. So graph, connect the dots. And I guess we should label those points. 3, 11, 2, 5, 1, 3. The y-intercept is 0, 2 1/3. And then -1, 2 1/9. So roughly, oh yeah, we're supposed to find the inverse. So replace f of x with y. Y equals 3 to the x minus 1 plus 2. Interchange x and y, so we get x equals 3 to the y minus 1 plus 2. Then we solve this for y. So one thing to remember, the inverse of an exponential function is a logarithmic function. So when we're finished, y should be equal to some logarithmic function. Okay, the first thing we do is subtract 2 from both sides. So we get x minus 2 equals 3 to the exponent y minus 1. And then we can convert this exponential equation into its logarithmic equivalent. The exponent is y minus 1. Remember, exponents are equal to logarithms. So the exponent y minus 1 is equal to the base 3 logarithm of x minus 2. And then we add 1 to both sides, so y equals the base 3 logarithm of x minus 2 plus 1. Okay, that's f inverse. I'll point out one other thing. The domain of this inverse, remember, arguments of logarithms have to be positive. So x minus 2 has to be greater than 0. And so the domain is x greater than 2. So the domain is from 2 to infinity. I'm messed up. It should be parenthesis 2 comma infinity, because x minus 2 has to be strictly greater than 0, which means x has to be strictly greater than 2. So we do not include 2. But remember how to find the vertical asymptote for a logarithmic function. So it involves the number 2. So the vertical asymptote is x equals 2. But it's below the x-axis. So I just want to point out, if y equals 2 is a horizontal asymptote for the graph of a function, then x equals 2 is a vertical asymptote for its inverse. So it's consistent with the concept of interchanging x and y. If I replace this y with x, then I get an asymptote for the inverse. So that's a little detail that can be helpful to remember. Okay, for the next function, sketch a graph of this exponential function, v of x equals 2 to the exponent x plus 2 minus 1. Okay, since we're subtracting 1 from 2 to the x plus 2, this means we have a horizontal asymptote of y equals -1. And it will be to the left of the y-axis where it's asymptotic. Okay, as far as picking ordered pairs, well, I'm going to pick them based upon the exponent, x plus 2, and then also the base of the exponential. So if I just start with x equals -4, then replace x with -4. -4 plus 2 is -2. 2 to the -2 is 1/4. And 1/4 minus 1 is -3/4. So just do the arithmetic one step at a time. Okay, so notice that this point will be above the horizontal asymptote y equals -1. And for this exponential function, all of the points on the graph have to be above y equals -1. Okay, the next x value I'll pick is -3. And then replace x with -3. -3 plus 2 is -1. 2 to the -1 is 1/2. 1/2 minus 1 is -1/2. And then I'll just pick integers that increase by 1 each time. So -2, -1, and 0. When x is -2, replace x with -2. The exponent -2 plus 2 is 0. 2 to the 0 is 1. 1 minus 1 is 0. So this is an x-intercept, -2, 0. Then replace x with -1. -1 plus 2 is 1. 2 to the first is 2. 2 minus 1 is 1. And then finally, when x is 0, 2 to the second is 4. 4 minus 1 is 3. Okay, so we can plot those points. Okay, so -4, -3/4 is about right here. I'll label those in a minute. We have a horizontal asymptote of y equals -1. Then -3, -1/2. It's about right here. -2, 0. -1, 1, and 0, 3. That's the y-intercept. So that's roughly the graph. So this point is 0, 3, -1, 1. This one is -2, 0. This point, -3, -1/2. And this point, -4, -3/4. Okay, now we'll find the inverse. So before finding the inverse, on this function, v of x, y equals -1 is a horizontal asymptote to the left of the y-axis. So on the inverse, I'm expecting a vertical asymptote of x equals -1 below the x-axis. So we'll see if that works out. So to find the inverse, write y equals 2 to the x plus 2 minus 1. Then interchange x and y, so we get x equals 2 to the y plus 2 minus 1. And then we'll solve this equation for y. So first add 1 to both sides, x plus 1 equals 2 to the y plus 2. And then we'll convert this exponential equation to its logarithmic equivalent. The exponent is y plus 2. So the exponent y plus 2 is equal to a logarithm. It's the base 2 logarithm of x plus 1. And then we subtract 2 from both sides. So y equals log base 2 of x plus 1 minus 2. Okay, so the domain of this inverse, so I'll write down the inverse notation, v inverse of x. Okay, the domain of this inverse, well, x plus 1 has to be strictly greater than 0, which means x has to be strictly greater than -1. So it's parenthesis -1 comma infinity. And the vertical asymptote is the line x equals -1. Just as we suspected. Okay, moving on. We have some compound interest formulas from section 3.2. Okay, so this one, the amount of $700 is used to purchase a CD that earns interest at the annual rate of 6% compounded monthly. The CD matures after 5 years. Find the value of the CD at maturity. So first, let's write down the function with an initial deposit of $700. So A equals 700. The annual interest rate is 6% and it's compounded monthly. So it's 1 plus 0.06 divided by 12. And then the exponent is 12 times t, where t is the number of years. This 12 is the number of times the interest is compounded, 12 times a year. Okay, so after 5 years, what's the value of the investment? So just replace t with 5. So we get 700 times 1 plus 0.06 divided by 12 raised to the 12 times 5, or 60. So this exponent is the same number as the number of times the interest is compounded in 5 years. So that makes sense. You can use a calculator to get a number that you can relate to on that one. Okay, the next problem, number 3. This time we're going to find the annual interest rate that's necessary for a deposit of $4,000 to grow to $7,000 in 8 years if the interest is compounded continuously. So first, let's write down the function, as much of it as we know. The initial deposit is $4,000. So A equals 4,000. And the interest is compounded continuously, so it's 4,000 times e to the r times t, where t is the number of years. We don't yet know what the interest rate is. Okay, but we are told that after 8 years, when t is 8, the amount in the investment is 7,000. So replace a with 7,000, set it equal to 4,000 times e to the 8r. We replace t with 8. Okay, now we're going to solve this for r. We see that r is in the exponent, so that means that we're either going to use a logarithm to solve for r, or we can probably just also convert the exponential equation into its logarithmic equivalent. But first we divide both sides by 4,000. 7,000 divided by 4,000, that simplifies to 7/4, or 1.75. So 1.75 equals e to the 8r. Since the base of the exponential is e, then let's just take the natural log of both sides. The natural log of 1.75 equals the natural log of e to the 8r, but the natural log of e to the 8r is just 8r. And so the interest rate is the natural log of 1.75 divided by 8. Okay, the next problem, this one says find the amount of time it will take for a deposit of $2,000 to grow to $3,600 if the interest is compounded once a year and the annual interest rate is 9%. So first we'll write down the function with the initial amount of $2,000. So a equals 2,000. The interest rate is 9% and it's compounded once a year. So it's 2,000 times the quantity 1 plus 0.09, and the exponent is just t, since the interest is compounded once a year. And we can simplify easily on the inside. We can write 1.09. I'll do that on the next step. Okay, but we want to determine how many years it takes for the value of the investment to be 3,600. So we replace a with 3,600, set it equal to 2,000 times 1.09 to the exponent t, and then solve for t. T is in the exponent, so we'll use a logarithm eventually. First, divide both sides by 2,000. And so that simplifies to 9/5, or 1.8. So 1.8 equals 1.09 raised to the exponent t. And then we can take the natural log of both sides. The natural log of 1.8 equals the natural log of 1.09 to the t. And then the exponent t can be brought out front, so it's the natural log of 1.8 equals t times the natural log of 1.09. And then lastly, divide both sides by the natural log of 1.09. So the natural log of 1.8 divided by the natural log of 1.09, that's measured in years. Okay, the next part, so this one says the height of a giant beanstalk seedling is 1.5 feet, and its height doubles every 10 minutes once it is planted. So find a formula for the height of the beanstalk t minutes after planting. Okay, so we'll create a column for minutes and then another column for the height. So at 0 minutes, that's the instant that the seedling is planted, its height is 1.5 feet. And we're told that its height doubles every 10 minutes. So in 10 minutes, the height will be 1.5 times 2 to the first. We've done this a couple of times. So let's just sort of cut to the chase. The height after 10 minutes is 1.5 times 2 to the first. But we can think of that as 1.5 times 2 to the 10 divided by 10. So the numerator of this is the number of minutes that have elapsed since the seedling was planted. And the denominator 10 is from the fact that the height doubles every 10 minutes. Okay, so 10 minutes after 10 minutes is a total of 20 minutes. And the height doubles again, so it's 1.5 times 2 to the second. But we can think of that as 1.5 times 2 to the 20 divided by 10. 20 divided by 10 is 2. But once again, I'll just point out the numerator 20 is the number of total minutes that have elapsed. The denominator of 10 is the number of minutes it takes for the height to double. Okay, so if we can see the pattern after t minutes, the height of the beanstalk will be 1.5 times 2. The exponent will be the number of minutes t divided by 10. So this is the formula for the height after t minutes. And you can check, you can verify that this is the correct formula just by evaluating it for different values of t. Okay, so the next example involves an investment that shrinks. An investment of $8,000 shrinks in value by 1/2 every 3 years. Find a formula for the investment's value in t years. Okay, so we'll create a column for the number of years and the value of the investment in another column. So we're starting out at t equals 0 years, the value of the investment is 8,000. Then in 3 years, the value of the investment is 1/2 what it was to begin with. So think of this as 8,000 times 1/2 to the first, which is 8,000 times 1/2 to the 3 divided by 3. Okay, so the exponent 3 is the number of years that have elapsed since the initial deposit. The 3 in the denominator indicates the number of years it takes for the value to shrink by a factor of 1/2. Okay, so let's do at least one more. 3 more years after 3 is a total of 6 years. And so the value of the investment will be 8,000 times 1/2 times 1/2, or 1/2 to the second. But we'll observe that 8,000 times 1/2 to the second is 8,000 times 1/2, and the exponent is 6 divided by 3. In the exponent, the 6 in the numerator is the same number as the number of years that have passed since the initial investment. The denominator 3 is the number of years it takes for the investment to shrink by a factor of 1/2. Okay, so seeing that pattern, we can write down what the value of the investment is after t years. It's going to be equal to 8,000 times 1/2, and the exponent will be t divided by 3. So that's the value after t years. Okay, we'll look at some logarithms. So these are, once you understand what a logarithm is, these are pretty easy. So evaluate each expression. Log base 2 of 35. Well, let's just say it's equal to x. And then convert this logarithmic equation into the exponential equation. 2 to the x equals 32. 32 is a power of 2. So 32 is the same as 2 to the 5th. And 2 to the x equals 2 to the 5th means that the exponents are equal because the base numbers are equal. So log base 2 of 32 is equal to 5 because 2 to the 5th equals 32. Okay, the next one is similar. Log base 3 of 1 over 81. So let's say that that's equal to x. Then convert that logarithmic equation into an exponential equation. 3 to the x equals 1 over 81. 1 over 81 is 1 over 3 to the 4th. And 1 over 3 to the 4th is 3 to the negative 4. And so if 3 to the x equals 3 to the negative 4, x equals negative 4. So log base 3 of 1 over 81 equals negative 4. Okay, the next one, it's along the same lines, but this is a little trickier. So log base 5 of 25 times the cubed root of 5. So let's say it's equal to x. Then the exponential equation equivalent, 5 to the exponent x equals 25 times the cubed root of 5. But 25 is 5 to the second, and the cubed root of 5 is 5 to the 1/3. And 5 to the second times 5 to the 1/3 is 5 to the 2 plus 1/3. So I'll just write 2 and 1/3. If you want, you can write it as 5 to the 7/3. That's okay. But since 5 to the x equals 5 to the 7/3, then x equals 7/3. So this simplifies to 7/3. Okay, the next one, log base 8 of 128. Let's say that that's equal to x. So convert the logarithmic equation into an exponential equation. 8 raised to the exponent x equals 128. Both 8 and 128 are powers of 2. 8 is 2 to the 3rd. So 8 to the x is 2 to the 3rd to the x. And 128 is 2 to the 7th. And 2 to the 3rd to the x is 2 to the 3x. And so, because we're multiplying those exponents. And 2 to the 3x equals 2 to the 7th. That implies that 3x equals 7, so x equals 7/3. So log base 8 of 128 is 7/3. Okay, we have a couple of minutes left, and that's enough time to find the domains of these two logarithmic functions. Y equals log base 10 of 5x plus 9. So 5x plus 9 has to be positive, which means 5x has to be greater than negative 9. which means x has to be greater than negative 9/5. So the domain in interval notation, parenthesis, negative 9/5, comma, infinity. And then one more, y equals the natural log of 7 minus 3x. Find the domain, so 7 minus 3x has to be positive. That means it's greater than 0. And 7 has to be greater than 3x. And so 7/3 has to be greater than x. But this just means x has to be less than 7/3. So if x is less than 7/3, then the domain in interval notation is parenthesis negative infinity, comma, 7/3, parenthesis. Okay, we're about out of time. Tomorrow, or not tomorrow, but Wednesday, we'll look at more problems. And in the event that we don't cover everything that I would like to, there are always those videos on YouTube that you can watch to see everything that you need to know. That's all for today.